about running the interactive experiments. So with that, today we are going to be talking about surface codes and quantum memory experiments because our aim is going to be to run a quantum memory experiment using the surface code on IQM resonance. Uh, just as a reminder, yesterday we had some structure of this workshop that looked like this. We started with a big picture overview of quantum error correction, so why we want to do it, what it is, and what the roadmap looks like. And we then talked about some simple quantum codes and decoding. So we looked at how quantum codes are able to detect both bit flip and phase flip errors, and then talked a bit about decoding and how decoders look, both at the software and hardware level. For those of you, I hope some of you got a chance to experiment with the notebook that was on GitLab or GitHub last night, which is kind of an intro to CRISP notebook. It should, if you've done any sort of programming quantum circuits before, it should be pretty straightforward to pick up. But I just got everything up and running, or sorry, I just uploaded the notebook for today as well to the GitHub. So there, and I believe that there also may have been. So last night there was a CRISP update. So some of the syntax may have changed slightly for connecting to the quantum computers. So that's been updated in today's notebook, but just be aware that there was a CRISP update, and so we have to adjust a little bit for that. All right, so today we're going to talk about the surface code and quantum memory experiments. So we want to know what is the surface code and what is a quantum memory experiment. We'll tackle those two things in piece by piece, and then we're going to spend some time working on the hands-on notebook. So we'll run a quantum memory experiment on IQM resonance. And then at the end, we'll have a little bit of time for wrap up, and maybe a little bit of brief discussion about future directions. For those of you who are interested in, for example, IQM's current research on QEC, I'm not going to really be able to go into that much, but would be happy to connect you all to the relevant people who can maybe give another seminar on the current research or something like that. All right. So with that in mind, I'm going to give a brief summary from yesterday, emphasizing some of the key points that I'm going to directly reference today. And then I'll talk about the surface code, and then talk about quantum memory experiments and what we're actually going to be trying to measure today. And so just as a reminder, please put questions in Q&A. I'm going to pause at the end of each of these segments to do Q&A. And there will be a break at the end of this talk before we start pivoting into working on the hands-on notebook. Also, for those of you who are not sure, the notebook is a Jupyter notebook. It will run just fine on Google Colab if you don't have anything set up locally to run Jupyter notebooks. But you will need either Google Colab or a local Python 3.11 or 3.12 environment in order to run the notebook. And I'll bring that up again at the break, so if people want to get set for that during the break, you can. All right, so a summary from yesterday. So the key idea of error correction was that we can take many physical qubits and kind of clump them together into one abstract logical qubit, where the idea is that we choose specific states of the many physical qubits to represent a 0 for the logical qubit and a 1 for the logical qubit. And we saw this in the simplest form in the repetition code. And the idea here was that the thing that we're trying to manipulate is 0 or 1, but quantum qubits and quantum gates are noisy. And so we decide to encode what we mean by a 0 as 3 physical qubits or more, which are all in the 0 state. And what we mean by a logical 1 is 3 physical qubits in the 1 state or more. And the idea then is that in order to manipulate the logical qubit, we can do different operations on the physical qubit. So in this case, to flip the logical qubit, we would need to flip all three physical qubits. But either way, we're able to do that. And we saw yesterday how by doing very carefully selected measurements using ancilla qubits, we were able to detect when errors occurred and sometimes correct them. The problem with the repetition code is that it doesn't detect phase errors, right? Phase errors where one physical qubit picks up a minus sign when it's in the 1 state and nothing happens when it's in the 0 state. And we saw that this caused problems when we put our logical qubits in superposition. So in order to deal with that, we talked about the 422 code, which is a very simple code. It doesn't actually correct errors, but it does detect them, where we encoded 2 logical qubits, so 4 possible states, in 4 physical qubits, which have a total of 2 to the 4th or 16 possible states. So we picked out these 4 special states as the logical states. And we were able to find out that because we put our physical qubits in superposition in order to represent a logical state, we were able to detect both bit flip and phase errors. And we did that by measuring various syndromes or stabilizers. The operators of stabilizer, the measurement's a syndrome, by measuring these ancilla qubits in between. So we use these data qubits on the corners here to encode the logical state. And we use the ancilla qubits as extra qubits that help us measure the information we need to detect whether or not an error has occurred. Now, speaking of which, how did we do that? We measure partial information, and it helps us identify the most likely errors. And the key point is that it doesn't destroy the encoded state, because as long as there wasn't an error, we get the same answer. And so no matter what we measure for these special bits of partial information, it just tells us error, no error. It doesn't actually destroy superpositions of logical qubits or anything like that. So we saw yesterday that the ancilla 1 was used to measure one syndrome. We should measure 1 if an odd number of data qubits are in the 1 state. For those of you who are familiar with this notation, that means we're measuring the Pauli operator ZZZZ, tensor product of 4 Pauli operators on the data qubits. And ancilla 2 was so ancilla 1 was responsible for finding bit flip errors, because if a single physical qubit flips, then we will end up with an odd number of data qubits being 1, and that tells us that an error happened. Likewise, ancilla 2 is supposed to be 1 if an odd number of data qubits are in the plus state, which is the equal weight superposition of 0 and 1 with a plus sign between them. And that's the same thing as measuring XXXX. And this was responsible for detecting phase flip errors, because if a phase flip error occurs on one of the data qubits, then we'll go from an even to an odd number of data qubits that are in the state plus. So by using these superpositions and by measuring both whether there's an odd number of qubits in 1 or an odd number of qubits in plus, we're able to detect both bit flip and phase flip errors. Now, remember also that the core problem of what we did once we did those measurements is we needed to decode them. We need to figure out what errors happened given what we measure, what syndromes we measure. And so the core problem of decoding was that we take a list of syndromes and turn it in by some algorithm into the most likely correction to fix any errors that may have occurred. Now, we talked yesterday about how there's both offline and real-time decoding. Today, we are not going to be touching real-time decoding. That is actually implementing experiments with real-time decoding is kind of one of the frontier problems in the field right now. There have been some experiments done that way, but not a lot, and so there's a lot of work to be done there. So we're just going to be working on offline decoding today. And if you remember, that meant that we collect all of our syndromes through the entire process of whatever we're doing, and then we figure out the correction at the very end, and in classical post-processing. And we saw one particular decoder yesterday, which was called a minimum weight perfect matching decoder. And what this did is it said, imagine that we have a grid which represents, roughly speaking, different possible locations for our syndromes to exist. So you imagine that you have some grid of syndromes. There's a little more to it than that, but we'll kind of come to that in a tangential way later. And so imagine then that we have we go through our process of quantum error correction and we find that some number of these syndromes find an error. Now, again, there's a caveat in here. This isn't quite what's actually happening in the graph. It's actually what's called detectors, but again, technical detail. The idea of minimum weight perfect matching is that you find the shortest possible set of paths that pair off all of these errors. And the basic idea here is that one of these paths corresponds to a set of errors. So, for example, one of these red lines might mean that we think that that a qubit that lives somewhere on that line got flipped. And so in order to correct it, we flip that qubit back. So it turns out that in these particular types in specific types of codes, namely topological codes, like the one we're going to see today, a surface code, this is the way that errors occur. You can always pair them off in these sorts of ways. And so essentially, figuring out what the correction is figuring out which syndromes we pair off, and that gives us a set of errors. So you can imagine that all of these red lines here correspond to a qubit that we have to go and flip. Now, this decoder doesn't naturally generalize to other codes, but people have built software packages that implement minimum weight perfect matching, and the surface code's a really nice code. So we're going to work with that today. So those are the key points that I wanted to remind you of from yesterday. So before I move on to introducing the surface code, let me pause and see if there are any questions. Let's see. Okay, one question is, does this minimum weight perfect matching thing worry about phase flips as well? Yes, so in principle, yes, you would have to worry about phase flips as well. And that does show up in the minimum weight perfect matching with a couple of caveats that aren't really important here. Let's see. There's a question about approaching the problem of doing QEC with FPGAs. What could be a possible research direction? So I think really the answer is, how do you integrate FPGAs with a quantum computer in order to do QEC? That's kind of the big picture research question. I don't really have resources on this for you, unfortunately, but I think the big question is literally, how do you physically do this? How classically tractable is minimum weight perfect matching? Extremely classically tractable, and that is why it's a very efficient decoder. So decoders are classical algorithms. We don't use quantum computers to do decoding. We use classical computers to do decoding, so we find the quantum corrections we need to make to the quantum computer. And so, of course, we do want that very, very efficient, to be very classically efficient. Let's see. In slide 11, when we find the shortest path, if we have two syndromes falling on the diagonal, we can find two shortest paths. So you're referring to, for example, these two here. There's another path over here that would be equally good. What happens if we select the wrong shortest path? The answer turns out to be that you get the same answer for whether there was an error in your logical qubit. So it turns out that many different physical errors can cause the same logical error. So as long as you fix the correct logical error, you don't have to worry about it. And so in general, there's some sort of, let's call it degeneracy here, where there are many possible errors that you could do, and you just have to pick one of them sorry, there are many possible errors that if you choose one versus the other, it doesn't cause a difference in the logical error. So the aim here is to pick any one of those representatives. It's kind of an equivalence class situation. Um, let's see. Do errors always occur in pairs in the surface code? Yes, they do. Uh, well, okay. In at the level of these matching graphs, yes, and broadly speaking, the idea is yes, they occur in pairs. There's a little bit of technical detail to that, but you can think of them as always occurring. Sorry, not errors always occurring in pairs. Syndromes always get flipped in pairs. So it's not that the errors occur in pairs, it's that the syndromes get flipped in pairs, right? We're making measurements, and so the of these syndromes, and so the idea is one error flips two syndromes, and so that's the key point that lets us use this minimum weight perfect matching business. Um, can I provide some reference research paper sources to get more insights? So I had a list of those at the end of the presentation yesterday. So I can put that back up at the end of the day today, if that would be helpful to you. Help me remember at the end of this today. Is this related to minimizing entropy in terms of information theory? I believe there is a way to cast this as minimizing entropy, correct? But I don't know the details of that. Are we doing offline QEC? So is offline QEC coding? I don't quite understand that question. Here we are going to be doing offline decoding. Also, syndrome mapping on the grid is unclear. Right. So the idea is that roughly speaking, these dots are each syndromes. I haven't gone into the details of that, and it's not really going to be very important for today. So I will come back to that. So I'm not really going to come back to that point, but I can talk about it in more detail at the end if there's time. What happens when the phase is changed continuously as opposed to a phase flip? So this is something that popped up a little bit yesterday. It turns out that when you measure the syndromes, you're forced to get an answer of plus or minus 1. And so what that will end up doing is it will you could be so one way to think about it is when the phase is changed continuously, you can think of that in a precise way of having almost a superposition of possible errors, of either a bit flip error or not, sorry, a phase flip error or not a phase flip error, in a rough sense. And so when you do the syndrome measurement, what it does is it collapses that superposition into phase flip or no phase flip. So when the phase is changed continuously, the very act of measuring the syndrome forces it to end up being forces you to end up with a discrete error instead of a continuous error. So QEC kind of helps itself go from analog to continuous in that sense. A question about the homework. Is there a PyProject.html or requirements.txt for the GitHub repo? No, there is not. So this is a limitation of the surface code. We've digitized a continuous error into a discrete error, is the question. No, it's actually it's not a limitation. So what's happening here is that when you do a measurement, it's not that you discretize the error. It's that you take a continuous error and you actually remove, like you physically turn it into, you take the error and it literally physically becomes a discrete error. It's not that you're processing it like it's a discrete error. It's that by doing QEC, you actually physically turn it into a discrete error. It's the same way that if you have a superposition, oh, thank you. If you have a superposition, let's say you have, um, a 20% chance of measuring 0 and an 80% chance of measuring 1. You will never measure that 80% chance in a single measurement of your qubits. What will happen is you do a measurement and you either get 0 or 1, and the qubit will actually change state into 0 or 1. So what's happening here is that even though there's continuousness in the error, by doing a QEC measurement, you end up forcing the error itself to turn into phase flip error or not phase flip error. So it's not a limitation. It's actually collapsing a superposition in a way that's actually beneficial to you. It takes a superposition of error and no error, and turns it into actually error or actually no error, so you can actually correct it more easily. It's not an instantaneous snapshot measurement in the time of a continuous process. It is actually causing a collapse of the wave function of your ancilla qubits, and this causes the errors on the data qubits to actually discretize. Yeah, it's hard without going through all of the math to see exactly how this occurs. I can try to spend a little time talking about this at the end today. Okay, so with that, let me clear that. Let me move along to to introduce the surface code now. All right, so what we're going to start by doing is talking about the stabilizers for the surface code. So we start our stabilizers all involve 4 data qubits, and there's going to be 2 types of stabilizers. There's an X stabilizer, which I'll represent with a gray circle here, and there's going to be a Z stabilizer, which I represent with a yellow circle here. So the idea here is that X stabilizers will all be like this. So ancilla 5, which I've called the ancilla 5 here, this one is going to be 0 if an even number of data qubits are plus. It's going to be 1 if an odd number of data qubits are plus. So this, just like our 422 code from yesterday, measures whether an even or an odd number of the surrounding data qubits are plus. But it's only the data qubits that are connected. We'll see that there's going to be more data qubits in a minute. The Z stabilizers, these yellow circles, are 0 if an even number of data qubits are 0, or an odd number, and they're 1 if an odd number of data qubits are 0. And so this thing is measuring ZZZZ, and it's just measuring the connected qubits. So let me show you what I mean by connected in just a second. But these are exactly the same stabilizers that we saw for the 422 code yesterday. But now there's going to be many of these stabilizers. So, oops, oh, yeah, sorry. So what's happening here is we have the distance 3 surface code encodes 1 logical qubit into 9 data qubits. So I've labeled these 9 data qubits 0 through 8 here. And these black lines will come in just a second. So we're using 9 redundant qubits to represent 1 logical qubit. And they connect in a very specific way. So we have X stabilizers, which are measured at these 4 specific spots. So we have an ancilla qubit, A0, which measures an X stabilizer that checks data qubits 0 and 1 only. So each ancilla only talks to the data qubits that it's connected to. And these gray circles are X stabilizers. So there's 4 different sets of data qubits that we're doing this even odd check for. And then there's 4 Z stabilizers, which do the same thing here. These 4 Z stabilizers are checking different sets of qubits, and they are also checking whether an even or an odd number of qubits are in the 1 state. So the gray circles are checking the plus or minus states, whereas the Z states, the yellow circles are checking the 0 or 1 states. So all the information is sitting inside the data qubits, and the ancilla qubits are just being used to measure syndromes. So you can count. This actually requires 17 qubits in total to implement. So there are 9 qubits that are storing the information, and we use 8 extra qubits to do the measurements. Okay. So actually, sorry about that. I have a quiz coming up, which I misanimated. Let me hide these really quickly for you so that you can actually think about these things yourself. So let's get a feel for this. So remember that we said yesterday that the logical states of a code are the ones where all of the stabilizers give 0, or all of the syndromes give 0. So in that case, let's just focus on the Z syndromes right now. So let's only focus on these yellow circles. And remember, they say 0 if an even number of the surrounding data qubits are 0. So go ahead and take a minute to think about some possible states of the data qubits where all of the Z syndromes are 0. So I'll give you just a minute to think.
Danny, if you have a slide with the
Oh, sorry.
for
I
this
didn't read the.
question, it might be helpful. I'm
My
not sure
mistake.
if it was intentional. Okay, no worries.
That was not intentional. Sorry.
Okay.
There we go. Okay, so just as a reminder, we're focusing on the yellow stabilizers here, these Z stabilizers, and we want to know how many states of the blue data qubits can you come up with where all of these Z syndromes are equal to 0. And so just come up with a couple of examples if you're able. And if you want to put an example, one of the examples in chat, feel free. Okay, so I'm not seeing answers, so let's take a look. Let's just focus in over here on ancilla 3. Let's see what an example state is that has the Z syndrome, this specific Z syndrome equal to 0. So this Z syndrome is 0 if an even number of the attached data qubits are 0. So how could that happen? Well, maybe both of these are 0. That's one state. And that would have ancilla 3 being 0. Or maybe both of these are 1. And that would also have ancilla 3 be 0. Right? Because there's an even number of attached qubits that are 0. So there's a very simple example for this, which is that all syndromes could be 0. Yes, as some people pointed, sorry, all data qubits could be 0. If all the data qubits are 0, then indeed we can check that certainly all of the yellow circles, these Z stabilizers, have an even number of zeros attached. Great. So that's one such state where we're going to say there's no error detected by the Z syndrome. But that's not the only one, right? We could also have a situation, for example, where all of the qubits are 0 down here. And then let's say just these two get flipped. So let's go ahead and check what's going on. So A3 has 2 zeros attached to it. We're good. A1 has 4 zeros attached to it. We're good. Sorry, A1. A4 has 2 zeros attached to it. Again, good. And A6 has 2 zeros attached to it. So we're good. So this has all of the Z syndromes equal to 0. Now, for an example of a state which would not allow this, if we just take that one qubit here and flip it back to 0, now A6 is unhappy, right? A6 has one data qubit that's 0. And so that is not, that would be an error state. That would be a state where the syndrome for A6 would come back 1, and the surface code would be telling you, hey, there's an error, something went wrong. And so let me give, so there's actually many different states of the data qubits that have all Z syndromes equal to 0, but not all of them. So let me just show you a few examples. So each of these, you can think of each of these here as a separate choice of states of the data qubits, right? So there's the all 0 state on this side. There's the 1111 state over here. Notice there's a little bit of a difference between these top and bottom ones here. So you should convince yourself that this state with all the vertical ones here equal to 1 is also okay. But notice there's an odd number of 1s here. And there's an odd number of 1s over here, and an odd number of 1s over here. But there's an even number of 1s in all the upper ones. So that's actually kind of an interesting thing, and we'll come back to that in just a second. But there are many possible states. There are, in fact, 2 to the 5th, which is 32 different states, which have no error detected by these Z syndromes. Okay, so it turns out then that we can take these states, which we are going to call good states, just so that I have some shorthand to call them. That's not a standard name. I'm just calling them good states. It's handy. And we can take those, and we now also need to make sure that there's no X errors. So we need to make sure, or sorry, no errors detected by the X stabilizers. So we need to make sure that these gray circles also read 0 in our logical states. And I'm not going to derive this, but it turns out that the 0 logical state should be thought of as the sum, the quantum superposition of all these good states, which have an even number of 1s in any row. So these are the same states that I showed you before, but they're now sorted into 2 sets. The blue ones, if you look at every row, got an even number of 1s in every single row. The 1 logical state is the sum of all the good states with an odd number of 1s in every row. So you see here, there's an odd number of 1s in each row in all of these cases. And now I specifically mention rows because this doesn't work for columns. There's some asymmetry here, and this has to do with the fact that this picture is not quite symmetric. If you rotate this by 90 degrees, a gray circle turns into a yellow circle. So it's not quite symmetric in that sense. So it's important that you're looking at an odd number of 1s in any row. So for example, this column has an even number of 1s, and this column has an odd number of 1s. So you shouldn't focus on the columns. You should focus on the rows here when we're looking at these states. Okay. And so this is what our logical 1 and our logical 0 is going to be. And so so then we have some questions, right? We have to ask, how do we tell if we're in the logical 0 or the logical 1 state? Well, we can just measure whether there's an even or an odd number of 1s in each row. If we're if we measure an even number of ones in every row, we're in state 0. If we measure an odd number of ones in any row, we're in the 1 state. And if neither of those happens, then we're in an error state. Okay. Yeah, so it's a fact that these states have all the X syndromes equal to 0. I won't derive that fact. Okay, so now we have an important question. We want to imagine doing a bit flip. So we need to turn the logical 0 state into the logical 1 state and vice versa. Otherwise, we can't manipulate our logical bit. So remember in the repetition code, we were able to do this by flipping all the qubits. So in this case, I'll let everyone think for a second. How can we turn, let's say, one of the states in the top row into a state in the bottom row? I saw the comment about the pen color. I'll try to change that in the future to make sure I've got better contrast. Good. So I'm seeing the right answer start popping up in chat. So the answer is that to get from a state in the top row to a state in the bottom row, we can flip the first column. So let's compare what's happening here. So if we flip the first column in this first one, it turns us into this state on the bottom here. And if we flip the first column in this second state, it turns us into the state in the second one. If we flip the first column here, then we end up getting to the state on the bottom here. So indeed, flipping a column of qubits is enough to get us from the logical 0 to the logical 1 state, because it just interchanges states in each of these rows. You can convince yourself that if you flip a column of qubits, that will always interchange a state with an even number of ones in each row with a state with an odd number of ones in each row. So flipping a column of qubits is logical X. It turns out it's actually okay to flip all the qubits too, but we're just going to use a column in this case. Now, I want to mention something very important here, a term called the code distance. This is the minimum number of physical qubits that are affected when you flip the logical qubit. So here, in order to flip the logical qubit, the smallest number of qubits you can flip to go from the top row to the bottom row is 3. It's a full column of qubits. If you flip any fewer, you'll be in an error state. But you can flip between the logical states with only 3 by only touching 3 physical qubits. So this is called the code distance, and that's why we call this particular code the distance 3 surface code, because its code distance is 3. Okay, so to that end, and I should mention that this also tells you, this code distance tells you something about how many errors you can detect, right? So this tells us that if there are 3 specific errors, then we get a logical error. We can accidentally turn 0 into 1. And so the code distance actually is the number of. So certainly you can't say that this code will detect 3 errors, because there's a set of 3 errors that messes up your logical bit. And so the code distance actually tells you, it's roughly speaking, half the code distance is the number of errors that you're able to correct. There's a -1 in there, or a floor function. So if there's a distance 3 surface code, then maybe that means there's a distance 5 surface code. And indeed there is. All we have to do is we have to grow this grid. So for any d, there's a distance d surface code that uses a d by d grid of data qubits. So here we have 1, 2, 3, 4, 5 data qubits, and then we connect them up with syndrome measurements in this alternating fashion that you can see here. And in total, to combine the data and the ancilla qubits, this requires 2d squared minus 1 qubits. And for technical reasons, we prefer that d is odd. There's there's a few weird technical limitations and also undesirable features when d is even. So this is actually a full family of surface codes, right? For any distance d, we can write down a surface code. And as we saw yesterday, when you use more qubits in your code, you tend to get better error correction performance. And that's what happens with the surface code as well. You can think of this as adding extra redundancy. So why is the surface code nice? The surface code is nice for several reasons. So first of all, there's a high threshold. So if I remind you all, yesterday we talked about a threshold, and that's saying that if your error rate is smaller than the threshold, then more error correction helps rather than hurts, right? And you can calculate the threshold for the surface code, and it depends on the exact noise in your system. It's something you calculate based on the code and the system. And the noise, and that's typically about 0.5% to 1%. Now, I remind you, classically, the repetition code had a threshold of 50%. So this is actually a tiny number compared to classical codes, but it's extremely high by quantum code standards. 0.5% to 1% error rate is about as good of a threshold as you're going to get for the most part. Another thing that's nice about the surface code is that only nearby qubits talk to each other, right? So we have this wonderful little grid structure of our qubits, and we don't have to have any faraway qubits talking to each other. And this is very nice because, especially in solid-state qubit architectures, it's difficult to make faraway qubits talk to each other directly. You end up having a large overhead in having that happen. So these codes, like the surface code, are very well suited to superconducting qubits and other solid-state qubit types. Finally, the surface code is extremely well studied theoretically. We understand a lot about it. And this paper from the archive here is the one that introduced the surface code in the context of error correction. And you'll notice that this paper was submitted in 1997. So theoretically speaking, the surface code has actually been studied for almost 30 years now. So there's a lot of machinery that's very well developed there, theoretically. Okay, so that's the overview of the surface code. We saw what types of stabilizer measurements we need to make, and we saw how we can implement logical bit flips, and briefly discussed why the surface code is nice. So let me pause here for questions on this segment, and I see a bunch piling in, so I will get to them as quickly as I can. Okay, so one person asked, is this the definition of logical 1 and 0 in general, or only for this particular use case? So specifically the surface code, we define logical 1 and 0 in this way. Actually, this is up to a basis transformation. You can do whatever basis transformation you want among these two states. But yeah, this is specific to the surface code. It's actually any distance surface code will have the same basic definition of logical 0 and logical 1. Okay. The data qubits, when discussing the logical 0 or 1, the data qubits are 0 or 1. Doesn't it lose some generality, as the tendency is to put it the H state to start with? So the idea here is that in the logical 0 and the logical 1, we are already in a superposition. So this plus here on the right-hand side, this is quantum superposition. It's not an or anything like that. This is a quantum superposition. So the logical 0 state is a large superposition of these 9 different qubits. It's actually a very entangled state of these 9 qubits. So there's no generality lost or anything like that. You also can do superpositions of the logical qubits if you want as well. Is X on any column, not row, related to the asymmetry of the code? Yes, they are. Is the 422 code a distance 2 surface code? It is. Very good catch. What is the drawback of surface codes? Good question. So surface codes require a large number of qubits to encode one logical qubit. So as we saw here, it takes 2d squared minus 1 qubits to get a distance d code with one logical qubit. That's actually that's a very large number of qubits. So in terms of qubit resources, they're actually quite inefficient. So depending on what your constraint is, you may want to use a different code. Good. Let's see. What are stabilizers? So stabilizers you can think of as syndromes. It's a measurement that you make that is detecting whether errors occur. So this idea of we're going to measure whether an even or an odd number of data qubits are plus, that's a stabilizer or so technically speaking, the stabilizer is actually this operator XXXX that corresponds to the measurement, and the syndrome is the 0 or 1 output, but you can think of syndrome and stabilizer as basically being the same thing. It's a set of measurements that you make that tells you whether errors occur or not. Isn't nearest neighbor a disadvantage for QEC? So that depends on the code. So if you only have nearest neighbor connectivity, then it becomes harder to do codes that require long distance connectivity. The surface code doesn't. So if you're doing the surface code for QEC, then nearest neighbor connectivity is perfectly fine. So the idea here is that the connectivity just needs to match between your hardware and the code that you choose. Are surface codes, speaking of which, are surface codes useful for movable qubit architectures like atomic qubit-based ones? So surface codes can be useful there. Usually with movable qubit architectures, they rely on different codes that match better to the strengths of those particular architectures. And so they tend to use ones that have a bit denser connectivity. Do you get an advantage if you wrap the opposite sides of the surface code so that every syndrome is connected to 4 bits? So that's an excellent question. So the idea here is imagine that we so actually what we would end up doing here, let's see, there's a parity issue that I'm running into here. Let me think about this for just a second. Yeah. Okay, so roughly speaking, the idea is imagine that this thing wrapped around here to come back to D3. This one wrapped around here to come to D0. So you have to be a little more careful than what I've done here, but yes, roughly that. So good, that's an excellent question. That is a different code called the toric code. And what the toric code does is something very similar to the surface code, but it encodes 2 qubits instead of just 1. And so that is an advantage if you decide, in some sense, you get 2 qubits instead of 1. The downside to this is that then you actually have to have these qubits laid out on the surface of a donut. So you can't draw it in flat space like this, and you can't have the connectivity in flat space like this. Let's see, would even D surface codes be like the 422 code? 2 qubits encoded with a degeneracy nightmare. So
Oh,
there is some degeneracy. It's not a nightmare, but it can be handled. The more pressing concern with even D surface codes is actually that it turns out they treat X and Z errors slightly asymmetrically. I can't remember off the top of my head which one they're better at detecting, but they're slightly better at detecting one versus the other. Um, and so we don't actually like that. Um, is D equals 5 the optimal distance for the surface code? It depends on what you're optimizing, right? Uh, so as you increase D, you will, as long as you're below threshold, get better and better performance. So D equals infinity would in principle be the best performance. But we don't want to use infinitely many qubits. So you have to define your optimization metric to talk about an optimal distance. Um, what is the difference between the color code and the surface code intuitively? That's an excellent question. So the color code, um, it just has slightly different layouts of the stabilizers. If I remember correctly, each stabilizer is connected to 3 qubits instead of 4. I might have that wrong. Don't take my word for that. I'm trying to do this live. Um, and so the encoding is just a little bit different, and so the error correction properties just behave a little bit differently. Conceptually speaking, though, they're actually closely related codes. Is there a way to improve the rate k over n of the surface code? So that's the number of qubits encoded divided by the number of physical qubits. So the surface code will always encode one logical qubit. In this is what I'm showing you is actually already an improvement over the base rate of the surface code. So technically, this is actually the rotated surface code. There's an unrotated surface code which requires more qubits. But in general, I'm not aware of a way to significantly improve the rate of the surface code, but that doesn't mean it doesn't exist. I just don't know it offhand if there is. Um, how do you measure the distance between qubits? So that if you're talking about the physical distance between the qubits, that depends on your hardware. You take a ruler and you measure the physical distance between the qubits. Um, how many effective logical qubits are for QEC? So the idea is that QEC, I'm not sure quite what the question means. Um, and the idea of QEC is that we're taking many physical qubits and turning them into a single logical qubit, and then we're doing computation with many logical qubits. So the aim is to use logical qubits because they're error corrected. Um, so physical qubits are bundled into logical qubits. How is the unrotated surface code different from the rotated surface code? So the qubit layout is slightly different, and there's additional stabilizers that are measured here. Um, it's uh, let's see. Instead of what's the best way to say this? So one way to think about this roughly is that let me think about that. Okay, so it's easiest to just look at a picture of the unrotated surface code versus the rotated surface code. So I encourage you to just take a look at a picture, and that should make it clearer what the difference is. The main conceptual difference, or sorry, the main practical difference is that the unrotated surface code uses more qubits. Um, let's see. So if there is 1 qubit error, we can have either 2 or 4 syndromes triggered. Is that true? Yes, that is true. So what happens, for example, if data qubit 4 has an error, if it has a Z error, we trigger ancillas 2 and 5. If we have, so this is a Z error. So X stabilizers pick up Z errors. And if we have, what's a good color? An X error, so then we end up triggering ancillas 1 and 6. Sorry, writing this is hard. And if we have a combined X and Z error, which is called a Y error, then that will trigger, so a Y error will trigger all four. So indeed, if one qubit is triggered, has an error, we can have 2 or 4 syndromes triggered. But the Y error ends up getting decomposed into an X and Z error. So roughly, you can think of each error as triggering 2 or 4 syndrome. Sorry, as always triggering 2 syndromes. There's a question how to perform transversal gates between code patches if every physical qubit in a chip is used to encode one logical qubit. So the idea here is that you would not use every physical qubit in the chip to encode one logical qubit. You would have one chip that has many different patches on it. And then you would be able to perform gates between the code patches that way. The question is Z stabilizer for bit flip errors, X stabilizer for phase flip errors. Yes, that's correct. So Z stabilizers detect bit flip errors, and X stabilizers detect phase flip errors. That's correct. How many logical qubits are present in the current generation of IQM quantum computers? So IQM Garnet, so on the cloud, IQM Garnet has 20 qubits. That's enough to fit a 1 distance 3 surface code. IQM Emerald has 54 qubits. That's enough to fit a distance 3 or a distance 5 surface code. And I forget if, I would have to double check if it's possible to lay out. There's enough qubits for 2 distance 3 surface codes, but I don't remember if the chip layout is compatible with that. But it depends on the code that you use. So very soon, we will have a 150 qubit machine out as well, which will allow for larger codes or more logical qubits as well at small distance. But this is actually an important point that I should say right now. If you are reading if you're reading specs about logical qubits, always, always, always ask what code are they using, right? The number of distance 3 codes you can fit into some number of qubits is smaller than the number of distance 5 codes you can fit into the same number of qubits. So when you're seeing all these specs about logical qubits, they always assume some particular code. And that code may or may not be a very useful or good code. So if I remember correctly, when IQM gives these specs, we generally benchmark it in terms of a surface code, but different companies will do something different. So please be aware that when you get those specs, they're assuming a particular code. Do superconducting qubits support long-range gates between different code patches? So in principle, you can build infrastructure for long-range gates. This is technically challenging for superconducting qubits, but it is something that is possible to implement. Let's see. Is lattice surgery useful in the real-world experiment scenarios, such as connecting multiple QPUs? So this is jumping to something that we're not going to be really able to cover in this introduction, but lattice surgery is a technique for taking multiple patches of surface code. So imagine you have a chip where you have 2 copies, enough qubits that you have 2 copies of the distance 3 surface code, and you want to do, or let's say 3 copies, and you want to do logical gates between them. So lattice surgery is a technique for those. Lattice surgery in general works on the same chip. So connecting multiple QPUs is not a useful technique. Lattice surgery is not a useful technique for connecting multiple separated QPUs in general. You have to have some very careful connectivity between them in order to do that. So generally, if you were to have multiple QPUs, you'd probably be implementing your gates between them in a different way than lattice surgery. But long-term, people are talking about doing gates using lattice surgery. Let's see. If you have a bit flip in data qubit 2, you have only one syndrome triggered. Right? Yes, this is correct. So here, if you have a bit flip on data qubit 2, then only stabilizer 3 or ancilla 3 gets triggered. And so then the question is, can minimum weight perfect matching be used? The answer is yes. And the that's where the subtlety comes in, that what you were seeing was not quite a graph of the stabilizers. So there's a little bit of a translation problem where you have to be very careful about how you construct that graph that I showed you earlier for minimum weight perfect matching. But that's an excellent catch by Ron Cohen there. Just so to help you when you're looking into this topic further, you'll notice there's a difference between some of these things on the edge. They're like these empty circles. These are called boundary nodes, and those have to do with the situation that you just talked about. Good. And then there was another question about whether the way that different errors can trigger different syndromes. So yes, it depends on the connectivity. So different errors on different qubits trigger different errors. So actually, in fact, if you had a Y error here, oops, that's not good contrast. If you had a Y error here, that would actually trigger 3 ancillas. So it is possible to trigger 3 ancillas. And so then, yes, thanks for catching that. And you have to be a little careful about that minimum weight perfect matching business. Okay, excellent questions. And I finally cleared out the Q&A. So let's move to the quantum memory experiments now. So what is the goal of a quantum memory experiment? The idea is, for a given logical state, so let's say we prepare the logical state 0, we want to determine how quickly logical errors occur. And then there's one other goal, which we're not going to work on today, but with big enough QPUs, you can check if you're below threshold. So let me explain that a little bit, both of these points. So here's the flow of a quantum memory experiment. And then we'll see what happens. Or sorry, how this achieves these goals. So what we're going to do is we're going to initialize a given logical state to start. Sorry, let me change colors because that's bad contrast. So we start by initializing a logical state. So maybe it's logical 0, maybe it's logical 1, but also maybe it's logical plus or logical minus, though that's kind of the standard thing to do, one of those 4. Then you measure the syndromes n times. So the idea here is that doing that measurement takes some amount of actual time. So measuring syndromes n times is a proxy for basically waiting and then checking, is there an error? Waiting, checking, is there an error? And so you say, okay, has an error happened yet? Has an error happened yet? Has an error happened yet? And those are physical errors. Then you measure your data qubits, and then we decode. So our data qubits are probably going to have lots of errors in them. But what we're going to do is we're going to use our syndrome measurements, plug them into the decoder, and ask, do we think a logical error happened? Or sorry, how do we correct the data qubits? So we correct the data qubits as part of the decoding process, and then we check, okay, at the end, did we get the same state we started with? So you'll notice here, all we're doing is we're saying, start with logical 0. Did we get an error? Did we get an error? Did we get an error? Physical errors. Decode, and then say, okay, at the end, did we end up with logical 1 or logical 0? Our hope is that we stored logical 0 and we got logical 0 out. So you can kind of think of this in the terms of yesterday. We had A and B. So you can think of A as being the one to initialize a logical state. And then B comes in here and says, okay, let me figure out what A stored. And we're going to check how many times B was right or not. And so that is the sense in which we are checking how quickly logical errors occur. We're just saying, did B get the right message? And if we change n, the number of times we measure the syndromes, that's like saying B waited a different amount of time. So over time, how does B end up with more or less errors? So what is the plot that we're looking for? So this is the plot that I made from the notebook that you're going to be running today. Let me walk you through what the aim of this plot is. So this is QEC round. That's how many times we've measured the stabilizers, right? So we go measure the stabilizers, measure or the syndromes, measure the syndromes, measure the syndromes, measure the syndromes. Each repetition is like person B waiting longer to retrieve the message. And then we measure that against the logical error rate, which is how many times B gets the wrong answer for what they think A stored. And so, not surprisingly, the longer you wait, this number is going to go up, right? If you wait longer and longer, more errors can happen. But the hope is that it goes up very slowly. Ideally, this number would be extremely small and grow very, very, very slowly, something more like that. Now, so this is the sense in which we see how fast logical errors happen. How many rounds does it take to basically randomly get 50-50s logical 0 or 1, and B is just guessing at this point what A stored. Now, there's this other thing here, which is that with big enough QPUs, you can check if you're below threshold. So what does that mean? So so here's an experiment that actually demonstrates being below threshold. So recall, being below threshold means that the errors are rare enough that more error correction helps instead of hurting. So here, now we have more to understand this plot. So the ones I want you to focus on are this, and this. So this experiment is doing this, is the exact plot that I just showed you. It's error correction round versus logical error probability for different code distances. So D equals 3 is a small surface code. D equals 5 is a bigger surface code. D equals 7 is a bigger surface code. And you'll see that the shape of these curves is the same for all three of the plots. But as we add more and more qubits into the code, let's say we look at time 100, the probability of an error goes down when we add more qubits. So that means that more error correction is helping, not hurting. So in general, you expect pretty bad performance from the distance 3 surface code. But once you get up to, say, distance 7, the performance has improved a lot. And in fact, it has performed better than doing no encoding, which is just, I have a qubit, let me store its state, and check later how well I've stored that state. And that's what's this dashed green line here. That's the best physical qubit. So just a single qubit, you store a 0 or a 1, and then wait and see what happens. So this plot is demonstrating being below threshold. You have to have a big enough qubit that you can, QPU, that you can actually see this performance, and your error rate has to be low enough as well. So just so you know, today we're going to get a plot more like this. And we're just doing distance 3, so we're not going to check threshold, and the performance is not going to be great because we're going to be doing almost no optimization. QEC really requires a lot of optimization. So today you're going to be doing the simplest QEC experiment, and then there's a ton of technical things that you can do to improve that performance. And you can get the performance significantly better on the same QPU. And that's even including simple software optimizations as well. Okay, so this is the overview of the quantum memory experiment. Basically, A initializes a state, B checks for errors, decodes, and then we say, did B get the right answer or not? And we check the probability that B got the wrong answer. So there's a few details that you're going to need to be aware of. So let me just highlight a couple of these. So when we initialize a logical state, how do we actually do that, right? So logical states are those for which all the syndromes are 0. And so imagine you initialize all of the qubits to 0. What do you get if you measure the stabilizers? Well, if you measure one of these stabilizers, then an even number of data qubits is always 0 because all the data qubits are 0. And so you just get 0. So that's good. But there's a problem, which is that if all of your data qubits are 0 and you measure one of these stabilizers, how many are in the state plus? Well, it turns out that the state 0 is equal to, I'm going to drop normalization here, plus minus, like this. Okay, if I put the normalization in, there's a 1 over square root of 2 here. But there's an equal chance that your qubit will be in plus or in minus. And so there's some quantum probabilistics going on here, right? So each qubit has a 50-50 chance of being in plus or minus. So actually, it turns out that when the Z stabilizers are all 0, but the X stabilizers end up randomly being 0 or 1, because you're basically randomly deciding which of these qubits is plus and which of these qubits is minus. And it turns out and so the way to think about this is that we end up with our qubits in a logical 0 state plus a random set of sorry, this should be Z errors. That's a typo there. A random set of Z errors. And it's errors that show up in these X-type stabilizers. And it turns out that that's okay. You just treat those as errors to decode later. So initializing the logical state ends up introducing a set of errors that can be decoded, but you just have to keep track of them and be aware of that. But all you have to do is to initialize the state. The logical state is to measure all of the stabilizers, and then you'll get a logical state plus some errors that you can track. Okay, when we measure the syndromes n times, this is a technical detail that I'm just going to flag because it's going to lead to a couple of annoying points. But so I black box the code that deals with this, but I just want to make you aware that this is an issue. So imagine that data 3 had a bit flip error, right? But no other qubits did. Assuming there's no further errors, let's measure our syndromes. So when we measure A1, what do we get? Well, if there's no errors, we should get 0. And if there's 1 error, that means that we have the wrong number of qubits that are 1 or that are 0. And so we should get a single error. We should get the answer 1. Okay. And so for example, imagine that we started out. Sorry, let me back up for a second. So imagine for simplicity that we started with 0, 0, 0, 0, right? And then we accidentally had an error in data qubit 3 so that this turned into 1. And so now we measure A1 and we get 1. So now we repeat. Now, if you remember yesterday, we said that when we do a measurement, what we're of the syndromes, we're actually not measuring A1 equals 0 if there's an even number of data qubits as 0. Let me actually go back a few slides and I'll emphasize this point. This was early. Oh, sorry, I don't have this slide in this slide deck here. What we ended up doing was we actually didn't say A1 is 0 if an even number of data qubits is 0. What we said is we're going to flip A1 if an odd number of qubits are 0. So when we do this measurement, we have 0, 1, 0, 0, and we run the circuit, we're going to measure 1. But then if we repeat the circuit, what actually happens is that we flip A1 because there's an odd number of data qubits. So we actually end up accidentally flipping it back to 0. And the reason that this happens is because we never said that we reset the ancilla. So technically speaking, if you want what I've put on the right-hand side here, if you want this to be true, then you have to reset your ancillas. Oh, let me type this. So must reset ancillas each time for this to be true. Because the circuit flips the ancilla if an odd number of qubits are 0. It doesn't actually set it this way. It just flips the ancilla. And so if you repeat it again, it's going to flip again and oscillate with no further errors. So just something to be aware of. The takeaway here is that if you don't reset your ancillas, one error that happens once will make your syndrome alternate. That doesn't mean that there's new errors, but that does mean that your syndrome is going to alternate. Now, one last bit of detail here. What information actually goes into the decoder? The time matching, which is the decoder toolbox that we're going to be using today, actually doesn't take in syndromes. It takes in something called the detector. And the detector is basically saying, did this syndrome change since the last measurement? And that's closely related to the point that we just talked about. And it's computed by XORing syndromes at different times together. And this behaves slightly differently when you have or don't have resets for your ancillas. So there's going to be some black boxed code here, which will deal with this for you, but it's just a bit of information that you should be aware of. Okay, so that's all of the material that I have to present for today in slide form. I'm going to take a little time to answer some questions, then we'll take a short break and spend pretty much the rest of the time working on the hands-on notebook. So I'm going to take about 5 minutes of questions, and then we can take a break, and I'll try to answer some of the other questions in text during the break. Let's see. So the first question here is, are all n rounds similar? Can they be different? So there's actually two versions of this question. Are these n rounds homogeneous? So the aim is actually for these rounds to all be the same, because the idea is you want to say, I have one QEC circuit that I have, and I'm going to go, let's go. I'm going to just repeat that over and over and over again, and I want to know how effective that is at tracking down my errors. So ideally, you want to make them as homogeneous as possible. There's another question, if n can be reduced, it can improve efficiency. No. So n here is that is part of the experiment. It's a proxy for the amount of time that you're waiting. Now, obviously, you would prefer in real life just to do everything as quick as possible. But the goal here is to see, of this experiment, is to see how long you can wait before you lose before B always gets the wrong answer, right? So n is not something that is n is something that we choose, but it's a proxy for how long we're waiting before B comes by and extracts A's qubit, roughly speaking. Let's see. So adding more QEC rounds. So somebody's asking, does adding more QEC rounds decrease the logical error? But the figure I showed is increasing. But when we're doing more QEC, the logical error rate, we want the logical error rate to go down. Okay, so there's two ways that we can talk about what is more QEC. So one is that we add extra qubits, more redundant qubits. So that is changing D. That's changing the number of qubits involved in the code. And so when we add more qubits, that means our error rate is going to drop. Now, no matter how good you are at catching errors, if you wait longer before decoding, more errors are going to happen. So the fact that this slopes upward is just saying that if you wait longer, more errors happen. That always is true, whether you correct the errors or not. So the trend that you're looking for is going from the red plot to the blue plot, light blue plot to the dark blue plot. And the idea here is that as we make the codes better and better, then we should be able to make this number down to, let's say, I don't know. So the goal is for this number on the y-axis to be, 10 to the minus 10 or something like that, right? So goal y-axis should be, right? So that even though if we wait longer, more errors happen, those errors are so tiny that we don't, they're so rare that we don't have to care. Mm. Okay, so there's a couple of other things here. Let's see. So what is the 2023 D equals 5 line here? So this experiment that I'm showing you here is from 2025. So in between, basically Google had done some hardware improvements between 2023 and 2025, and probably also software improvements, so that this curve running the exact same experiment turned into this curve. So that's just showing their hardware improving over time. Let's see. The different D equals 5, there's other D equals 5 plots. So here, this is doing multiple different D equals 5 codes in the same, I believe in the same device. So I think they can fit 2 D equals 5 codes on the same device. And so that's why you're seeing multiple ones there. Let's see. Good. Is resetting a qubit slower? So when I talked about the reset or no reset thing here, so the XORing is classical. It's extremely fast. This is all classical computation. Ancilla reset is slow. So the aim here for us is going to be to not reset the ancillas, at least for the experiment that we're doing. We'll get better performance because the reset is very slow, and that's a bunch of time where more errors can set in. Can I elaborate on detectors? Is it like a qubit or a group of qubits? So a detector is a mathematical construct. So okay, so let's back up. So a syndrome takes in data from either 2 or 4 qubits in this case, and says error or no error. A detector just says, since the last time you checked, did an error happen? So that's all the detector is doing. It's just, it's not saying, was there an error at some point? It's, was there a new error? since the last time you checked for errors. So that's the only difference between a detector and a syndrome. Let's see here. Okay, so with that, I'm going to try to answer the other questions in text right now. Let's go ahead and take that 15-minute break. But while I do that, let me leave this up so that people can. So in GitHub, there is a file that is surface code NERSC participant. That is the one with the exercises. So you get to try building pieces of the circuit yourself. If you just want to look at the solution and submit everything, you can do that. You can do that with the solutions notebook. So just so you know what's there. So you go ahead during the break. I encourage you to try to get that notebook set up either in your local Python environment or in Google Colab.
Thank you, Danny. So maybe we take a small break also for you, and then we come back.
All right. Shall we get started again?
Yep, I
Um,
think we're ready to continue.
okay.
Please go ahead.
All right. So welcome back, everyone. Um, so now comes the time to actually start running things on quantum computers. Before we get into the notebooks, which I will get into in just a minute, I just wanted to showcase a little bit on IQM resonance, just so that you know how things work. So the machine we're going to be mostly using today is IQM Garnet. So this is what happens when you log into, if you go to resonance.iqm.tech and log in. If you haven't logged in, sorry, and you'll see this. If you haven't made an account yet, I put the link in chat for to get bonus credits so that you can run your experiments, run lots of experiments. Um, so uh, right, so when you're here, we're going to be working on IQM Garnet. It's a 20 qubit machine, and with the qubits connected like this. And so if you want to see anything about one of the qubits, about the qubits, you can see, for example, the single qubit gate error here is 0.07%, and the two qubit gate error is a little higher there, but it's 0.53%, 0.48%, something like that. You can see the performance of all the different qubits on the device. And take a look at Emerald and Sirius as well. Just quickly flagging that Sirius is a very unusual one. We have all-to-one and one-to-all connectivity, which there's actually a lot of interest in specialized codes for this sort of architecture, that it's quite different from ordinary QPUs. So just something interesting to take a look at. Now, the most important thing here is that if you want to run something on the quantum computer, you're going to need an API token. And in order to get your API token, all you have to do is click your initials at the top right here, um, and then click on your, oops, sorry, not your name. Click on your organization if you're, let's see. Wait, where did this go? What is happening here? Where did the tokens go? I think something has changed on the website since the last time I looked at it. That is peculiar. Um, my apologies. This is slightly embarrassing. Um, okay.
There is a
Okay. Yeah,
comment that
good.
says to click
Down
on the
here.
name.
Okay,
Yeah.
sorry about that. Yeah, so go ahead and come here, click on your name. Right, the token management system changed just a week or two ago, and that's what happens. So if you just scroll all the way down here, you can create a new token using this button. And so if you create the new token, you can name it and you'll get a token that you just copy and save it somewhere. If you ever need to delete or create a new token, you can do that in the same place. So go ahead and just make sure that you create a token there. Um, all right. Yeah, I don't. The token will last for a year by default, so you don't have to worry about your token expiring and anything like that. But if you lose it, just go back and make a new one. The tokens won't cost you anything. All right. So sorry about that slight hiccup. I had forgotten that that changed. All right. So let's go take a look at the notebooks. So I'm going to be running this in Google Colab right now, um, but you can run it obviously in your local Python environment. There are a couple of images that are on the GitHub. They don't show up here, unfortunately, so I'm going to start the tutorial in my local environment just because those pictures are going to show up better. So give me just a second to swap over to that. All right, good. So what we are going to be doing today is running a distance 3 surface code memory experiment on IQM Garnet. And so the idea here is that we have these 20 qubits that are laid out like this, and we're going to use 17 of them to build a surface code, which is laid out like this. So you'll notice that this layout actually fits very nicely onto IQM Garnet. I think all we need to do is forget about qubits 3, 18, and 17. And then we will end up with exactly this graph. So these graphs look basically the same. And so here I've changed colors a little bit. Data qubits are still in blue. Z-type stabilizers are in orange, and X-type stabilizers are in purple. So the first thing you'll have to do is install CRISP, which is the language that this is, the SDK that this is written in, as well as matplotlib if you haven't already, and PyMatching. So PyMatching is for decoding. And IQM client is responsible for letting you send CRISP programs to the IQM quantum computers. So what we're going to do over the course of this notebook is each of the little pieces of the experiment is going to be broken up for you. So for example, I'm just going to overview right now. And this is meant to be self-contained, but I'm just going to talk through it right now. But we're going to start by measuring a stabilizer. And so this first thing that we're going to do is have a function that measures a z stabilizer and a function that measures an x stabilizer. And then we can test out those functions on various things. Then we are going to write a function using those that measures all of the stabilizers in the distance 3 surface code, right? Because the aim of the experiment is measure the stabilizers, measure the stabilizers, measure the stabilizers, and then decode at the end. So that'll be the first thing that we're trying to do. Then we're going to write a function that initializes either a logical 0 or a logical 1 state. And oops, I forgot to delete this from the participant notebook. This line is the answer. It's not supposed to be in there. That's what's supposed to be in there. Just noticed that. As well as this part, as well as these parts. So this is actually supposed to be in here. Sorry, I started from the solutions and didn't remove some of these pieces. Okay, so we'll talk about initialization, and then we'll do one round of error correction. And finally, we'll write the memory experiment that is going to initialize the qubits, perform error correction, and then measure the data qubits. So that's the sequence of things that we'll do. So those are the things that you'll be writing, and then we'll submit it to real hardware. And then the decoding comes at the end. So the decoding is a little bit technically involved. So I've written the decoding code for you. But for those who are interested, please feel free to look into all of it and unpack all of that yourself. So it's all there, but there's a lot of detailed bookkeeping and things like that in order to pass the results of the experiment into the decoding. So a bunch of predefined functions, and then we'll actually decode and plot the results at the end. So that's where we're headed for this experiment. So let me pause before I continue to see if there are questions about the structure of what this interactive notebook is going to look like. Oh, sorry. Which screen am I currently sharing? Is this am I sharing Colab or am I sharing virtual via code right now?
The screen shows a notebook where it says Surface Code NERSC Participant IPyMB. It's a Jupyter notebook. We can see
Okay,
the
got it.
picture.
So
Yeah.
I'm sorry, I was scrolling in the wrong thing. I was scrolling in Colab. I didn't notice that. So So sorry, let me just go briefly back through the notebook. So we're going to start by defining functions that measure stabilizers. Then we're going to define functions that measure all the stabilizers. Then we'll define the initialization down here, initialize logical state. Then we'll define one round of QEC, and finally the whole memory experiment. The rest of the notebook is going to consist of running the experiment on real hardware and then processing the data at the end. So down here, this decoding with pi matching part, that part is all this is all the pre-written stuff for you. But at the very bottom here is going to be the cell where we actually do the decoding. Compute logical error rate. So that's just a preview of where we're headed. Okay. So with that in mind, I encourage anyone who's starting right now, please run this cell. It's going to take a little while to install the packages if you haven't already installed the packages that you need. Okay, so the first thing we want to do is to measure a stabilizer. So the idea is that we want to, sorry, let me just make this a little bit clearer, is +1 is 1 if it is 0. Okay. So the idea is that we want to initialize the ancilla qubit to 0, and then we want to flip the ancilla qubit if the stabilizer we're measuring is 1, and leave this ancilla unchanged if it's 0, and then measure the ancilla qubit. So we're not going to worry about the initialization and the measurement quite yet, because that happens when we actually build the full circuit. But our aim here is going to be to construct quantum circuits that measure the Z and X type stabilizers. So we're given data qubits, which is, so in CRISP, you can think of a quantum variable as just an array of qubits, and an ancilla qubit, which is 1 qubit. And the result is that we want the ancilla to get flipped if the Z-type stabilizer gives you 1, and it does not get flipped if the Z-type stabilizer gives you 0. So if you remember, yesterday we actually talked about that. Let me pull out the slides for that real quick. So I can show you and share that. We had a slide that looked like this. Let me get this shared. Right, so we have our ancilla that starts in state 0. How do we flip it if an odd number of data qubits are 1? Does anyone remember the key operation for this one? Good, I'm seeing the right answer in chat. It's a CNOT or a controlled X gate. So what we want to do is we want to do a controlled X gate, controlled on each data qubit and targeted on the ancilla qubit. So if we want to do that in CRISP, let me go back to the notebook. What can we do? All we have to do is say for qubit in data qubits, we're going to do a controlled NOT gate. So in CRISP, that's implemented as CX. So we just do CX and we say our control gate, which is going to be the data qubit, and the target is going to be the ancilla qubit. And that's all we have to do. because that implements the circuit that we said, right? So let me actually just run this real quick. And so, for example, oops, let me run that kernel. It's going to take a minute to do the imports from CRISP. So I make some data qubits, and I make an ancilla qubit, and I'm going to measure my Z stabilizer. And you'll see that when we print the ancilla, just a second here. It's going to say that that ancilla is always going to be 0. So why is that? Because we initialized our data qubits as 0, and so we will always get 0 for our ancilla. But if I print the quantum session of ancilla 1, it shows me what the circuit I've done is. So you see that we've implemented the circuit that I just showed you on the slide. It's a control X gate between each data qubit and the ancilla. Right. So here, let me pause for questions on what on this function here. There's been an ask for a PyProject.toml update in the repository. I will try to get that set up in the future for you. I don't have one handy right now. Sorry about that. Okay, so now let's say we want to measure an X stabilizer. So the key thing here is that for an X stabilizer, instead of flipping the ancilla if a bunch of qubits are in, if the data qubits are in the state 1, we want to flip the ancilla qubits. So the goal, flip the ancilla qubits if qubit if if each data qubit is in the state plus, right? So we still want to iterate over the data qubits. But the question is, what operation do we want to do? So we still want to flip the ancilla qubit. And so the operation we're going to have to do is still a controlled X operation, because we need to do X on the ancilla. But the idea is this. Imagine that the data qubit, so imagine the data qubit is, this is if minus, is minus. We could use a controlled X gate if this were minus, if this data qubit were 1, right? So how do we turn the data qubit from minus into 1? What gate does that? So the trick is to turn the data qubit into the state 1, do a controlled X gate like before, and then turn the data qubit back to its original state, right? So that's the idea. We don't want, we can turn the data qubit into a 1, do a controlled X gate, but we don't want to manipulate the data qubit, so we should flip it back at the end. So the idea here is what's going to do that. So what gate turns one into minus, that's the Hadamard gate. So we apply a Hadamard gate to our qubit, and then we flip the ancilla so this turns plus into 0 and minus into 1. This part will flip the ancilla if the data qubit is now a 1. And then we undo what we did to the data qubit, right? So we've h of qubit turns plus into 0, but then h of qubit again undoes that so that our data qubit's back to its original state. So these are the quantum circuits that make it so that the ancilla flips if the stabilizer is supposed to be 1. And it doesn't flip it if this ancilla is 0. So this is one of the more complex things that we want to be doing, one of the more conceptually complex circuits we're going to be creating here. So I'm going to pause and ask for questions about this. So one person just said, can you explain it again? Good. So let's start with the Z stabilizers. So the idea here is that for each data qubit, we flip the ancilla if the data qubit is 1. No flip if the data qubit is 0. Right? So what does that do? So the end result is that if an even number of data qubits are 1, the ancilla doesn't get flipped, right? Because if we flip the ancilla 0, 2, or 4 times, then there's no flip. If an odd number of data qubits are 1, the ancilla does get flipped. And that's what we wanted, right? That's the goal. That's the stabilizer that we're trying to measure. That's going to give us the syndrome that we're looking for, right? So that's the idea of the Z stabilizer piece. The X stabilizer piece is the same idea. We're going to do exactly the same thing, but our goal is to do the flips if the data qubit is in the state minus instead. And so the trick here is that we're going to take minus and turn it into, if our data qubit is minus, we're going to turn it into the state 1 temporarily. Then we can repeat the same process. So what happens here? So the end result is for each data qubit, if it's minus, we flip the ancilla. And so if an odd number of data qubits are minus, the ancilla gets flipped. So if you take a look back through the slides yesterday, this circuit is exactly there. And we can visualize that circuit by printing the printing the QS, the quantum session. Is what prints the circuits here. What happened here? It's called ancilla qubit, not ancilla. Oops, what happened here? I see. 2. Do this with data 2. There we go. Okay. Oops. Why did that behave this way? Oh, I see. Yeah, it just printed both circuits. Good. Yeah, so no, it didn't. What just happened? Data 1. That's what's happening. Sorry about that. Okay. So here is our first circuit. This is for measuring a Z stabilizer. And here is our second circuit. It's the same thing with a bunch of extra Hadamard gates in there. And if we look at the full scrollable element, we can see the whole circuit. So the only difference between these two circuits is the extra Hadamard gates. Let's see. If you're getting an import error in Colab, then you're going to need to make sure that you do the pip install cell up here. Or make sure that in your package manager of choice, you've installed IQM Client Crisp. Oops. So somebody asks an excellent question here, which is, I thought that the whole point of QEC is that we only do gates on the ancillas, but you did an H gate on the data qubit. That is true. The key point here is that the CX gate doesn't change the data qubit's state. And so if we do an H gate and then do another H gate, H undoes itself. If you're doing H twice, undoes it. So the idea here is that we temporarily modify the data qubit, and then we unmodify the data qubit. So it's true that we modified the data qubit, but we undid that with this extra line here. Let's see, if you already did the pip install and you're still getting import errors, then try getting rid of this capture line here and seeing what happens. It may be that for some reason you're having problems actually running the pip install. I'm not sure. It could have something to do with your Python environment. So yeah, I'm sorry. In the future, I will get an environment set up that you can that will make this a little more reproducible. Okay. And a question, how does entangling the data qubits with the ancilla qubits measure the Z stabilizers? That's what we said before. So this process here produces entanglement between the data and ancilla qubits. So in a way such that for each data qubit, if it's if it's minus, we flip the ancilla. If it's 1, we flip the ancilla here, and if it's minus, we flip the ancilla here. So that is measuring the stabilizer. Good. Okay. So there's another piece here, which is an optional task for you all, which I would encourage you to play around with. This is just one thing that I want to point out. This will be handled for you by the CRISP transpiler. But if you want to think a little bit if you want to be able to do some optimizations, this is an interesting thing to think about. So IQM, our device, our native 2-qubit gates, basically the ones that are implemented directly in hardware and are the most efficient gates to apply, are control Z gates, not control X gates. And so that means that our circuit will be more efficient if we're able to, or we'll actually be able to optimize the circuit better if we replace any of these 2-qubit gates with CZ instead of CX and single qubit gates. So this is an optional task for you to play around with, to rewrite those functions in terms of CZ gates instead of CX gates. So I encourage you to play around with that. I'm not going to do it here. Okay, but now comes a big piece. Now, once we've defined these functions here, our aim is to measure all of the stabilizers that show up in the surface code. So let's start with how many stabilizers are there? Well, let's take a look. Here's the surface code. And blue is data qubits. And the other colors are correspond to stabilizer measurements. So we can count that there are 8. There are 8 ancillas, and so we should have 8 stabilizers, right? So the idea here is that we're going to, and 4 of them are Z, and 4 of them are X-type stabilizers. So this thing down here had better involve measuring. So we're going to measure a Z stabilizer with some stuff, which we'll fill in a second. But there are going to be 4 Z stabilizers. Indentations are hard sometimes. There are going to be 4 Z stabilizers and 4 X stabilizers. And we just have to figure out what we want to put in each of these function calls. Oops. Oh my goodness. The spacing is atrocious. Let's just do it this way. Code's being a little funny. Okay. So for each of the stabilizers that we want, let's see what our stabilizer function looked like. It took the data qubits that are involved in that stabilizer and the ancilla qubit that we're looking for as the arguments. So the aim here is going to be to choose the correct data qubits, certain data qubits, and certain ancilla qubits out of the collection of all of them. So the input to this function is all 9 data qubits and all 8 ancilla qubits in the function. And our aim is to choose the right one, the right data and ancilla qubits, so that we measure the stabilizers we're looking for. Right. Okay, so it looks like, so I'm just going to point out in chat, it looks like people are adding pip install crisp separately, and that causes things to run correctly. I'm surprised, but because I was able to get it to run on Colab earlier without doing that, but yeah, whatever works, definitely add pip install crisp. So I think what people are suggesting, or restart the runtime. You may need to do pip install crisp as well. I'm not sure about that. Okay. So the idea here was that we want to measure each stabilizer. So what data qubits are involved in the first state in one of the Z stabilizers? Well, let's go take a look. Z stabilizers are in orange, we're told. And so one of them involves data qubits 0, 1, 3, and 4. So let's put those data qubits in here. It's going to be data qubits 0, 1, 3, and 4, right? Because those are the qubits involved in one of the Z stabilizers. And which ancilla qubit measures this particular stabilizer? If we go look at the layout, the ancilla qubit in question is ancilla 1. So we're going to use ancilla 1 to measure one of these Z stabilizers. So this is actually going to kind of indicate what's going on. If we look at this plot here, there's a Z stabilizer for ancilla 1, ancilla 3, 4, and 6. So those are the ancilla qubits that are going to appear in this part here, in the measure Z stabilizer calls. The rest of the ancillas are going to measure X stabilizers. So 0, 2, 5, and 7. And this is just coming from staring at the way that the code is laid out, right? So we have an X stabilizer at each of these orange circles, and that's these particular ancilla qubits. So, for example, ancilla 3 is connected to data qubits 2 and 5. So why don't we put that in? We're going to measure a Z stabilizer that involves data qubits 2 and 5 and ancilla qubit 3. Then we're going to keep going here. So let's see. Oh, I can't remember this off the top of my head, unfortunately. 3, 4, 6, 7. No, sorry, 3, 6, and then 4, 5, 7, 8. So 3, 6, and then 4, 5, 7, 8. So those are the qubits that are involved in the Z stabilizer measurements. And that's just from staring at how the code is laid out. So you can go through and read off the same things for the X stabilizers, but let me pause here for questions about anything so far, because this is the idea that so this measure all stabilizers together with measure Z and measure X stabilizer will cause us to measure all of the stabilizers, which is exactly what we want to do. All right, I'm a little bit concerned that there's no questions because that might mean that everyone's confused. Um, let's see. Does it matter that some of the stabilizers operate on 2 qubits and some on 4? So good question. So it depends on how you design these functions, right? So if we were to say something, if we were to design our function instead of this, if we were to design our function as doing the circuit super explicitly, Cx of data qubits 0 ancilla qubit, and then Cx data qubits 1 ancilla qubit, so on and so forth. Then we would have a problem that some of the stabilizers operate on 2 qubits and some operate on 4. But if we implement it with the for loop like this, then it doesn't matter how many qubits are in this data qubit thing. Just for each of them, we're going to get a CX gate. And so if you plug in 2 data qubits into here, then you'll get a stabilizer that acts on 2 data qubits. If you plug in 4 data qubits here, you'll get a stabilizer that acts on 4 data qubits. So that works just fine. By the way, there is a solutions notebook available. So if you want to scroll through at your leisure, go ahead and take a look at that solutions notebook. I'm actually going to switch to that later in the session so that I can just run everything super cleanly. Does the actual QPU hardware at IQM have this surface code layout? This is the actual QPU, IQM Garnet. So this picture, and let me see if I can zoom out. I think code doesn't like me zooming out for some reason, VS Code. So this picture and this picture are almost identical. There's just a few extra qubits in IQM Garnet. So yes, the actual QPU at IQM has this surface code layout, just with a few extra qubits in there. IQM Emerald has 54 qubits, and it has patches that look like this. So yes, this is actually how the QPU is laid out. This is the schematic of the actual QPU. Let's see. Um, for physical qubits, do the 2 and 4 qubit stabilizers accumulate errors at different rates? That's an excellent question. So in principle, yes. You're doing fewer gates on the so gates are noisy, and so the QPUs are sorry, the stabilizers that only involve 2 data qubits will have fewer errors on average. That's something that actually gets built into the decoder. Can you tell us about the basic architecture of quantum computers at IQM? IQM quantum computers are superconducting quantum computers, and they so I'm not sure what you want to know about the architecture, but here is the architecture of one of them. This is IQM Garnet. And if you take a look on IQM Resonance, you can take a look at some of our other quantum computers that are on the cloud. The quantum computers we install on site are very similar to those that are on the cloud as well. If you have a more specific question, I'm happy to talk about that. All right, so let me carry on a little bit here. So I'm not going to fill out the rest of these. I'll leave that as an exercise to make sure that you understand what's for you all to make sure you understand how this works. But if you're looking for solutions, check the solutions notebook. To which end, let me actually switch over to the solutions notebook right now. So that's going to make my life a little bit easier here. Oops, that is not the solutions notebook. That was my slides. There we go. Okay, so a little bit of this is the measure all stabilizers function. It's just been completed. I did it in this way just to be a little bit to write it a little bit differently. But we can run this in simulation. Oops, and I somehow missed my import. Oh, I had the same problem as you all. For some reason, this time when I ran it on Colab, it didn't work. Peculiar. Okay, so that's going to run. Let me just get this all running for when the install fixes. Okay. So now we're going to talk about initialization. So let me actually delete this for the moment. Hide this for the moment. So what do we want to do? What did we talk about doing when we initialize? So in order to initialize, we start by creating data qubits. And so the way we create our data qubits is as a quantum variable. So that's basically just a list of 9 qubits. And here's our ancilla qubits. So we're going to create the qubits. Now, if we want a logical 0, we said that if you remember back from the presentation, we just said that all we have to do, so we just need to measure all the, so no matter what we do, we will need to measure all the stabilizers. This will initialize our state into a logical state plus some errors. And that is what shows up down here. So that's this part here. We have to measure all the stabilizers. But if we want a logical 1, we have to do something, right? Because if we start from 0, when we apply those stabilizers, so what's the difference between a logical 1 and a logical 0? So remember, logical 0 says logical 0 has an even number of zeros in each row. And our data qubits will always start off as all 0. And so if we want a logical 0, we don't have to do anything. We started off with one of the states that appears in that big old superposition that I talked about. But if we want a 1, we had better do something. We had better make this not the case. So remember, we said that logical 1 has an odd number of zeros in each row. And so we do that by, if you remember, flipping the first column of data qubits, right? So we do that by saying we're going to apply an X gate, so a flip to each of the data qubits that are 2, 5, and 8. So why 2, 5, and 8? If you go look at the labeling, which I have now lost, let me see here. Do I have that file here? I don't. Okay. Let me pull it up in the GitHub. Okay, so if you take a look back in the layout here, oops, not that one. The first column of data qubits is data qubits 2, 5, and 8. So to go from all zeros to one of the states that we want in our logical 1, we would apply an X to 2, 5, and 8. So there's a good question here. Where are the measurements in the measurement function? It only includes gates. The measurements come here. So for example, here, after measuring the stabilizers, we're actually calling to call the measure function. And the reason for this is just tracking. This measurement can go in different places, but we actually it's more convenient to measure all of the ancilla qubits at the same time than to measure each of them individually. So we're going to be adding in the actual measure call as we go now. So good question. Let's see. Why don't we try to keep all ancillary qubits to be working on 4 data qubits? Doesn't ancillary qubits with only 2 qubits be more susceptible to error? It's the other way around. If there's only 2 qubits, then there will be fewer errors. Sorry, 2 qubits per ancilla. There will be fewer errors that way. But then if we only use 2 qubits per ancilla, that restricts us what we can do. That restricts very strongly what we're able to do. It's very, very hard to build an error correcting code from only 2 qubit stabilizers like that. Okay, let me make sure that everything up here ran correctly. It did not. Why did that run? Why did that not run correctly? Restart session. Let's try that. Okay, the fact that this is taking a while probably means good things. Yeah, it's because it's actually doing the big import. Yeah, so if you're still having problems, restart your runtime, and it should work. Yeah, there we go. Now we're up and running. Okay. Okay. So once we've gotten this initialization set up, you can play around with both initializing 0 and 1. You can see the quantum circuit. There's a bunch of gates going on here. There's Hadamards, there's CZ gates. I'm using the solution notebook, so I've actually rewritten these as CZ gates instead of CX gates, and a bunch of measurements. But now let's see what happens. We're going to um, do a test where we're going to run. So the way we're going to run this is we're going to take ancilla.qs dot run, and this is going to run in simulation. So here's what we run in simulation. So these are supposed to be the syndromes after initialization. So all zeros means we've actually prepared a logical zero, and everything else, we've got some errors in there. And remember, we talked about this at the end. There were some, there's a pretty good chance that we're going to introduce some errors in that initial measurement process. And that's okay. It's just going to involve correcting those later, decoding those later. Now, I'm going to offer as a question to everyone to think about. This is a list of measurement values for the ancillas. So some of the ancillas, if you look carefully at this list, are always 0. And this is a noiseless simulation, just remember. And some of these ancillas are always 1. Or sorry, can be 1. So one question is, which of these are always 0? So I'll give you a minute to think about that first. Ah, thank you. Somebody pointed out that what I did in the participant notebook, where I did data qubits 1, 2, 4, or 5 or whatnot, doesn't actually run because they go to a tuple. You actually need to do this nested for thing that I had here. Yeah, so sorry, this is the problem if you do the coding live. So yeah, you actually do need to do this funny list comprehension thing in order to slice the quantum variable. I think if we use the data type quantum array, it might actually work correctly, but I would have to check that. So yeah, put that in here. I see a question about what is introducing errors in the simulation. It's not actually an error per se. It's something like an error. So what's happening here is that when we measure an X stabilizer, if you remember, we said before that we're going because the qubits start out in the states 0, and the X stabilizer asks about whether or not qubits are in the state plus. There's some quantum randomness that comes in here. So basically what's going to happen is that the X stabilizers are going to randomly be 1 or 0. Because 0 is a superposition of plus and minus, and so there's quantum randomness when we do this measurement. And so you can treat that quantum randomness like an error and decode it later. But it does turn out to be but this is unavoidable in this situation, unless you want to have a really complicated circuit. Okay. So, yeah, so this is the same thing here. Okay, so that's kind of a subtle point. All right, so now what is involved? So now we have all the tools we need. So what is a QEC round? What happens in one round of QEC when that we talked about earlier? Well, all we do is we measure all of the syndromes. So we can have a function, which is, let's do a round of QEC. Let's measure all the stabilizers and then measure the ancillic qubits. So there was a question earlier, where is the measure call showing up? It's happening here. If you want to do it a little bit differently, you can, but that's how I chose to set this up. And so now the goal here is to put all of this together into the memory experiment. So what's that supposed to do? We initialize, we have a certain number of rounds of error correction, and then we read out the data qubits. So how do we do that? Well, fortunately, we've written all of those functions already. So we start by initializing the logical state that we choose. So we're going to input whether we want to put 0 or initialize 0 or 1. And we initialize. And that's going to spit out the data in ancillic qubits. And then we just do a QEC round, number of rounds times. Then at the end, we measure the data qubits, and then we'll return the qubits. So CRISP actually operates so that you don't have to return the measurement results, just so you know. So just putting in measure will output the measurements automatically. So that's it. This is the full memory experiment. It's this. We initialize the logical state. We do a number of rounds of QEC rounds. Then we measure our data qubits, and then we'll decode. The decoding will come later. So I've written a little function here that's just going to split this data up for you. So if I run this here, I'm doing 4 rounds, a memory experiment with 4 rounds. And what's happening here is that this parse result just spits out the results. So each row here, is an outcome. So we started in simulation. So for example, remember we said that in the first round, in initialization. So this is the syndromes we measure in initialization. And then this is syndrome round 1, syndrome round 2, syndrome round 3, syndrome round 4, data qubits. And so we get a whole bunch of measurement results. Now, there's some randomness in that initialization round, and there's some randomness in how the data qubits come out at the end. Those are not errors, those are quantum randomness. But this part we can treat like errors. And so we can just find out what all of the results are. But doing this in simulation isn't very interesting because there's no actual errors. There's no errors, just that funny quantum randomness at the beginning. So let's actually run this thing on hardware. So to connect to IQM Garnet, all we have to do is this. So there's a couple of extra imports, but and I'm adding a little piece which is going to mitigate certain errors. But we tell CRISP where the quantum computer lives. You put your token in. So here I've actually used Google Colab secrets to store my token, just so that this isn't going on a recorded YouTube session. My token doesn't appear there. I don't want everyone using my account to run circuits indefinitely into the future. So you can just put your token here, or a token here instead. But I'm just managing my token a little differently from you. And then we connect to the quantum computer by making this IQM backend call. We just say we want to connect to Garnet, and I'm adding these compilation options, which just add a little bit of extra stuff. And then we're going to say, for the initial state 0, we're going to create a memory experiment for a certain number of rounds. And then all we have to do is call run tell it how many shots go into running that circuit, and tell it to use the quantum computer. And if I go ahead and run this, it's going to take a little bit of time. Actually, let me check the queue on Garnet right now. Oops. It's taking a little bit of time to connect, I think. I think something's just running a little bit slow in here. I'm not sure what it is. It's not the quantum computer. The quantum computer hasn't found out that we sent anything yet, because I would have a job that shows up here. There we go. So now we see that I've started submitting some jobs. And they have started to show up on Garnet for me. So everything's done, and I printed out the actual results we got for running 0 rounds of error correction. So what you're seeing here is the actual results returned from the quantum computer. So this is the initialization and syndrome measurement, and this is the data qubit results. So I can show you as well. Where are we here? When we run with 1 round of QEC, we have the initialization here. We have the first round of syndrome measurements, and then we have the data qubit measurements. And so we just have a big pile of binary strings that have been returned from the quantum computer for us. So once we've done that, the rest of this, I'm not going to go into any details. This is just implementing decoding. This is meant to be, so if you read through this, it will tell you what's actually happening here. But the main thing that's happening here is we're calling from pi matching this decode function. And that is what runs that minimum weight perfect matching thing. There's a bunch of pre-processing and other stuff that has to happen beforehand, including this thing called building a matching graph. So this is a bit more involved in decoding than I can actually cover in the 15 minutes we have left. But if we compute the logical error rate for each of the jobs that we sent to the quantum computer, we end up with our error rates. So this is different QEC rounds and logical error rates. That's based on the jobs that I just ran on the quantum computer. And so that actually completes the result. That is the quantum memory experiment. So that was a lot, and it'll take some time. So I encourage you all to play around with the notebooks on your own. Make sure that you actually run it on the quantum computer, because it's much more interesting that way than running in a noiseless simulation. Okay, so I see a question, is 1,000 shots arbitrary? Yes, 1,000 shots is fine for this. It'll get you reasonable results. Yeah, that should get you some pretty reasonable results. If you use more shots, it probably won't change things too significantly. All right. So with that, let me pause for a second or let me go back for a second and tell you and remind you what we've actually accomplished. So we built the memory experiment. The memory experiment involves initializing the logical state, doing some number of rounds of QEC, which is going to be a variable, and then measuring the data qubits. And by doing that for many different numbers of rounds, we were able to get a plot that looked like this, where we said as we basically remember QEC round is like time, so we wait for a while before retrieving the message we stored. How much error do we get in retrieving that message? So if we don't really wait, then there's a very small error rate, and so our initialization procedure isn't perfect, and our measurement procedure isn't perfect, but we have a pretty low error rate if we don't wait. The longer we wait, the more error comes out until eventually we just kind of get noise. And so from this, you can extract that, roughly speaking, you get about 20% logical error rate every time you do a QEC round. Now, that's not very helpful, but again, we've done basically zero optimization. So good QEC requires a lot of optimization in the circuit construction and a bunch of things going down the stack as well. And I would encourage you all, if you're interested, to really think a lot, to really dig into the literature and start learning more about what some of those optimizations look like. For those of you uh, who are interested, one of the main places to start is to look at implementing this fault tolerantly. So we haven't done this fault tolerantly. We've just done QEC without being careful about the fault tolerance issues we discussed yesterday. So there's a bunch of optimizations that start there. But there's a lot of other things to pay attention to as well. So with that, I'm going to leave the rest of the notebook as basically something for you all to play around with. But there it is, running an experiment on the actual IQM device. So with that, I think maybe the best thing to do here is we only have about 10 minutes left, is to basically just pause to just stop for questions. I'll wrap up by saying that it was a really amazing to be able to present this workshop to you all, and you all gave lots and lots of amazing questions. I just have 74 questions answered already on today, listed as answered today. I had a huge number yesterday as well. So this has been a real pleasure. And if you have questions or are interested in anything in the future, please feel free to send me an email or connect with me on LinkedIn. With that, let me wrap up and leave some time for questions.
Yeah, and on behalf of all the attendees, I want to thank you for these 2 great days of presentation and this marathon of presentation. I don't know if you can see, but there's a lot of people who are using the reaction to show you appreciation.
Oh, excellent. Thank you all. Let's see. Oh, yes, I'm starting to see that now. Thank you all.
Oh, okay, yeah.
All right. Great. So I'll stick around for a few minutes to answer questions. So there's a few good questions coming up here. Let's see. So one question is how do I translate QEC round to time units? Okay, so that's something that actually so QEC round is some unit of time. But how much time that actually takes is something that requires digging into the pulse level access, because you actually need to know for one round, like we have a circuit, which for one round of circuit looks something like this. Let me pull it up here. It's, let's see. Yeah, it's a circuit that looks approximately like this. It's some very large, messy circuit. And in order to actually find out how long that takes, you have to dig into so this circuit is not what gets sent to the QPU itself. What gets sent to the actual QPU is a sequence of electrical pulses. And there's some compilation that goes from this circuit down to the electrical pulses. Electrical pulse level. So you actually have to like dig into that. So one of the nice things about IQM systems is that they are open. So anyone who has so who has one of our systems does have pulse level access, and that's actually very unusual. Um, so we give full pulse level access. So if you have an IQM system and you have pulse level access, you will have pulse level access to it, and then you can translate that to time units. If you have a paid resonance account, you can also do pulse level access as well and start digging into some of these sorts of things. Why does the logical error rate seem to be converging to a value around 46% rather than 50%? That is actually a very good question. And I'm not sure about the answer to it. I would have to think about that carefully, but this is a power law convergence. It's possible that there's just some random fluctuations here that are um, that are just taking you away from being a little bit closer to 0.5. It's possible that it's just the power law slows down around QEC round 4 or something like that. Um, but actually, let me see what happens. I'm just going to run this again for, let's say, 10 rounds. Somebody also asked, on average, how many credits are consumed for sending the job one time to the back end? So each of these, oh, why did that only go to, I sent 6. I don't know why it sent me less. Okay, let me clear this out. So for each of these uh, iterations here, there's one job sent to the QPU, and that job costs about one credit. So this is not going to consume very many credits. So I just consumed about 10. That's with 1,000 shots. If you go up to 10,000 shots, it's going to be more.
By the way, Danny,
Yes.
before I forget, you had mentioned about putting back the slides with the references for QAC that you showed
Yes.
yesterday. So perhaps we
Yes.
can do it at some point.
Yeah, let me actually do that now while this is running. I don't know if some of you are also running on Resonance. Maybe there's a queue, but let me see here. Was from this presentation. Let me just pull this up. Here. This slide had some of the references that I like for QEC. So please take a look at that. All right, so how do I debug connectivity to the IQM backend? I'm running the cell with my token and it's been running for 9 minutes, but I don't see anything on my Resonance dashboard. That is very peculiar. Um, let's see. So if it's still, make sure that there's not another cell running earlier. If that cell has been running for 9 minutes, that sounds like something that's not actually the back end itself. That sounds like something funny happening with either your internet connectivity or maybe something. Oh, I think I might know. So my understanding is that the very first time that CRISP runs anything on the back end, it takes extra time because there's something that gets compiled and saved to disk in the software. So it's possible that if this is the first time you're running, CRISP is doing a bunch of hard work there. And then hopefully every time in the future, it should be very quick. So I apologize if that's the case. Um, let's see. Oh, so multiple people are just getting 4 rounds. Let me take a look at what's happening here. Um, let's see here. What is going wrong? Did I rename a variable? Um, let's see. Result list. Okay. Let's see. Okay. Oh, I see what happened. So if you're trying to run the plot, the very last plot in the notebooks, you'll notice that the X ticks only go to num rounds. So num rounds is not what we want. It's max. Let's see, it's max. It's num. Sorry, I think I renamed this variable at some point. And so it's num rounds max. So the X ticks are incorrect in the very last one. I will fix that in GitHub. Um, but yeah, I think wait a second. Num rounds max. What is happening here? Yeah, and that's in both the X ticks and the axis. Um, Yeah. So if you fix the x-axis, so this is for Alec Lindman's question in particular, um, the plotting at the end is what's messed up. It should not, the x-ticks and the axis should not say num rounds. It should be num rounds max. Um, if somebody wants to go further in QEC, can there be a seminar and webinar arranged in the near future? So keep your eyes peeled. IQM is definitely interested in this sort of thing. So definitely keep tabs, and hopefully we'll be able to do something like that in the future to go deeper. Um, the IQM Garnet shows one job in the queue. Does it allow parallel processing from multiple users? No, Garnet does not have parallel processing from multiple users. It only has the 20 qubits that it has. And so if you're doing something with those, if one user is doing something with those 20 qubits, another user can't. So unfortunately not. Um, what are your suggestions for someone who wants to work in this field but comes from a classical machine learning background? Um, let's see. Um, so classical machine, okay, so there is an interface with classical machine learning already, which is that there are machine learning based decoders. So if you dig into classical machine, or if you start learning about machine learning based decoders, that's probably a good place to start from if you're doing a PhD in classical machine learning and want to work on this. Um, and so that will give you the uh, you'll still have to learn a bunch of stuff about decoders, but that'll get you a foothold where you can really do something useful early on. Um, let's see. Um, is there, let's see. There's a couple of questions about careers and things like that, which I'll answer in text. And that wraps up the other questions. So if you still have an outstanding question, I'm going to get to you in just a second, and uh, I will answer in text. And there's one or two comments left in there that I think were meant to go into chat. Oh, I'm seeing what are some research trends and open problems in QEC? Um, Basically integration. Um, People have lots of decoders. People have built QPUs. People have talked about, sorry, it's translate. I would say the big open problems are really translating the well-developed theory in QEC onto actual hardware. So right now, there's a lot of hardware level optimizations. There's a lot of workflow optimizations. There's and things like that. Though that's really I think the place that the field is pivoting into now, because we're just getting to the point where the hardware is really able to run meaningful QEC experiments, and get useful and interesting results on that. So yeah, I'm going to wrap up now and answer a few more questions by text, but or by typing the answer. So if you can close the meeting, if you can not quite close the meeting yet, Ermal, so I can answer those real quick,
Yeah,
that would be
yes,
great.
for sure.
But thank you all very much. I hope you enjoyed the sessions.
Yeah. Once again, thank you. And we will put this on YouTube later in the week. For people who are interested, you can search for NERSC training events on YouTube, and also on our webpage, we do post links. Thank you all, and thank you, Danny. We will leave this open for a little bit more for you to answer questions, but I will stop the recording now so that we can save it.